So today we're going to look at how to analyze complicated circuits. So the aim of this sort of subsection of the course, or whatever it is so this couple of weeks is that I want to be able to give you pretty much any circuit at all. I don't know whether the right hand side of that one's visible. Any circuit at all, and I need you to be able to tell me all sorts of things about it. So, for instance, I need you to be able to tell me how much, if I were to put an ammeter here, how much current it would measure if I put an ammeter literally anywhere else in the circuit. So, I don't know, here. Let's call that A2. This one can be A1. How much current would be there. I need you to be able to tell me what voltage, what potential difference I would measure across any one of these resistors or across the whole circuit. So basically, I want to be able to ask you for voltages and currents anywhere in this circuit. All right, so, and anywhere in pretty much any circuit. With the idea being that then you would be able to go away and design a circuit. So flip the logic a little bit, which could give you any amount of current or any amount of voltage on any particular part. And eventually we'll get to designing circuits for achieving very particular purposes. So for instance, if you need to run your washing machine at 35 volts and you've only got 120 volt resistor, 120 volt supply, then how would you run that thing and so forth. Okay. So what we're going to look at today is a thing called equivalent resistance. So when we have multiple components in a circuit, what is their overall resistance together? So if we look at this, whole section here, this with the two parallel arms, and then one of those parallel arms has a parallel bit inside it as well. If we imagine sort of throwing a blanket over this whole section and saying, how much resistance is this whole little bit here providing in addition to this 100 ohms to the circuit? We're going to look at a method of sort of working through a circuit by redrawing and annotating. So sort of visually just like simplifying and simplifying and simplifying a circuit, almost analogous to working backwards through an algebra problem. So there's sort of a way that we're going to analyze these circuits, and then we're going to use a few things called Kirchhoff's laws to check our results. Now you can use Kirchhoff's laws from the start, but I'm going to use Kirchhoff's laws as sort of a check at the end. Okay. Does anybody have any questions before we begin? I can see the chat's got something in it. Oscar, you're here. Okay. I don't really want to go back to the roll now, so I'll just make a note to change it. Has anyone else arrived in the last minute and a half? Okay. And Lewis, which part of the textbook are we on? That's a good question. We're just starting the chapter on analyzing circuits. So we are not on the VCAA website. Oh, I must have closed the window. We are. What? What the hell? This just happens to me about 1 in every 10 times I log into the textbook. It's just not there. What? Yes, there we go. So we're up to, so we've looked at electrical physics is really just laying the groundwork. What is charge? What is energy, voltage, all that sort of stuff. We're just starting practical electrical circuits now. So how can we design electrical circuits? And if we do have a particular design, how do we analyze them and look at how much stuff's going through them? So we're going to start by trying to just get down some rules for how we work through a more complicated circuit. Okay? All right. So I might we'll come back to this in a moment. But first off, we're just going to look at how do we calculate equivalent resistance in parallel. And we've done it, we did it in the video by just looking at a whole circuit which had a parallel component on it. And I just kind of treated these two things as I realized that if we put a particular voltage on here, let's say 12 volts, then because no voltage is used up in the wires themselves, that tells us that at that point there, the current still has 12 volts. And since we got 0 here, we know that that point there has 0. And then we can say, well, if we have to take a path through this resistor to get from 12 to 0, well, then we must have lost 12 volts on that resistor. So that resistor, if we were to measure it, would have a 12 volt drop across it. But then the same could be said of this path here. So remember, voltage is a resource that you're consuming. So if we consume it by going down from 12 to 0 via that path, then once again, the only place that energy could have been lost was on that resistor there. So that means that guy there must have 12 volts on it. But that argument's not going to work if we have another resistor in here. Because if we have another resistor in here, then we're not going to know what that amount there is, which means we go from unknown to 0. So each of these guys becomes unknown. So if we have an extra resistor in here that's not part of this parallel setup, then that argument that we made in the video kind of goes out the door and we're back at square one. And so we need to sort of go back to working out what is sort of the equivalent resistor for this section here. Okay. So here's what we're going to do. I'm just going to get rid of the battery, get rid of that other resistor, and just focus on that little parallel section. All right, and we can imagine the whole rest of the circuit is over here, but we're just going to look at this section here, and we're going to apply Ohm's law, but we're going to apply it in a kind of clever way, using just general voltages and general resistances to get a rule for what the overall resistance of this is. So what we're going to do is we're going to take this and we're going to say, what is that equivalent to if we were just going to put one resistor into our circuit? Okay, so what is the equivalence? What is the equivalent one resistor we could put in here that would exactly replace this parallel setup of two resistors? Okay, please stop me if that's not making any sense. Okay, please say so. All right, so what I'm going to do is I'm going to say this is R1 here, and this is going to be R2 here, and I'm going to call this guy over here RF for R effective. So the idea is this one resistor here is effectively the same resistance, does the same job as having these two in parallel. Okay. Now I'm going to put some amount of voltage on this circuit here. So,
John just told me that he thought it was at 9:45 and he's coming on right now.
okay, no worries. I'll add him to my list as well. So I'm going to put some amount of voltage on this circuit. So the idea being that when the current comes in, it's got some voltage V, and when it comes out, the current's got some lower voltage. So let's call that V1 and that one there V2. And I'm just going to call the difference between V1 and V2, so how much we've lost on this section here, I'm just going to call it V. Okay, I know it gets a little bit confusing using like V's for everything and R's for everything and I's for everything. There's always more than one. But so I'm going to call the drop across this whole section here V, and I'm going to call the amount of resistance R1 and R2, and I'm really not going to talk about V1 and V2 ever again, other than just in introducing V there. Okay. No worries. I've got a certain amount of current passing through here, and I'm going to call that I. And then I is going to get split up into two parts, and you're going to have I1 and I2. They're going to go through their separate resistors, and then they're going to recombine to form I again. Okay? Then I can say, okay, well, what's going on this equivalent side here? Well, I is the same. We don't have to worry about anything ever splitting on this side, and we can talk about there being a potential drop of V on this side. Can you guys see a fly buzzing around my eye? It's like driving me absolutely crazy, but I don't know if it comes off on the webcam. Keeps on coming back for more. Anyway, okay, so we're going to look at this situation, and the aim here, remember, is we want to work out for a given R1 and R2, what is this RF that does the same job, okay? So we're going to use Ohm's law, and we're going to use Ohm's law by starting with the observation that I is equal to I1 plus I2. Okay, pretty simple, right? So the two currents that are in the two sections, they've split off and they recombine to form I. So we're adding them together, we get I. Hopefully that makes sense. Okay, and then we can ask, what are those? What if we write these I's using Ohm's law? Well, using this argument from the video that we made the other day, we can see that if we put V across all of this, we've got a voltage drop across all of this. Well, that voltage drop is the same whether we go through R1 or whether we go through R2, because you don't lose any energy in wires. So the only place you can lose energy is in the two resistors. And if you start off with a certain amount of energy here and you have a certain amount of energy here, and how do you account for the difference? Well, you either went this way or you went this way. So either way, each of those resistors must be taking that same amount of energy, V. So how do I write I1? Well, it's going to be V over R1. So that's just Ohm's law rearranged with V as my voltage and R1 as my resistance. This second one is just going to be V over R2. Okay, well that's just the same thing for that second one. All right, what about this side? Well, we could look over here and we could say, well, wait a minute, the total amount of current we get is just going to be that same V, but divided by our effective resistance. So this one here is going to be V over RF. And then we can say, wait a minute, we've got V, 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 and we can just go through and we can cancel off all those V's. So we end up getting 1 over the effective resistance equals 1 over R1 plus 1 over R2. And it's really important that we understand that that rule came from when we set up these resistors in parallel. Okay? Let's just very quickly, for completeness, talk about another situation. The other situation is you put two resistors in series, but we already know the rule for that. If we have R1, R2, and we want to turn that into an effective resistor, RF, we've seen what we do there. We just add the two. So we say RF in that case is just R1 plus R2, because each electron has to get through both barriers. If you start, let's say the current's going this way, so each electron which starts here has to move through R2 and then R1, so it faces both resistances, so we just add them up. Okay, so when the electrons have a choice in parallel, the effective resistance is like this. When they don't have a choice and they have to go through both, the resistance is like this. Okay. So how do we use that idea to analyze complicated circuits? All right. Well, somehow I've lost my sheet. There we go. Okay. So we're going to look at this circuit here. And remember, let's say our eventual aim is to get this one here, A1, and that voltage there, V. And so we know that we know what this 100 ohms is doing, and we know that if we could just get all of this, if we could just write all of this as one effective resistance, then we could just add those two resistors and we'd be able to work out the total amount of current. Okay? So, how do we do this? Okay, what we want to do is we want to start by looking at the circuit and thinking of it as a series circuit of effective resistors. So we want to think of this as this resistor plus some effective resistance for this complicated bit. And so the eventual aim is to write this circuit, I'm going to put this down in this bottom corner here, as 100 ohms and something like this. Okay, and when we look at this and we say, okay, well, can I apply directly any of my rules to this situation here? Can I just look at this and say, oh, is this just a parallel circuit? Is this just a series circuit? Can I just crunch any of these resistors down? And you look at it and you say, oh, well, not really, because I don't have any just two sitting next to each other, right? But what I do have is this little section in here. We could use our parallel rule to work out what's the effective resistance of just that bit. Okay, so then that's going to let us write our circuit as something that looks like this. We're going to have our 150 ohm one here, and we're going to have something here, where that something represents this whole orange section here. Maybe I'll color it in orange. There we go. And those two come together, and then we have our 100 ohm one
Isn't it
here.
only 50 ohms? So?
Oh yeah, sorry, thank you. Yeah, thank you. I was looking at that one, but it's only 50 ohms. Sorry, thank you. So we have our 50 ohm one here, and then we move like that. And then in going from this one to this one, what are we doing? Well, we're taking both of these now, the 50 ohm and the mystery ohm, and we're crunching those two together to get this. Okay, so the idea is we start with the most inner parallel a little bit, and we just keep crunching them together into little effective ones until what we end up with is just a series circuit. And then we're going to work backwards from there to get all the measurements we want. Okay, so let's do that. We're going to, first off, we're going to try and find this orange resistor, right? So R effective for the orange resistor. All right, how do we find that? Well, we're going to apply our parallel rule to these two resistors here. So 1 over our orange effective resistance is going to be 1 over 150 ohms plus 1 over 75 ohms. I often find it's useful to try and factorize anything you can at this point. So I'm going to pull out 1 over 75 ohms, and that's going to be outside of 1 over 2 plus 1. See how that makes things a lot easier? And so 1 over R effective is going to be 1 over 75 ohms, and this is going to be 3 over 2. And then if we've got no additions in here anymore, it's all just multiplication here, then that means we can use that rule where we just take the two sides of an equation and flip them both. So that means R effective is going to be 75 ohms times 2/3 equals 50 ohms. All right, so this orange resistor here is going to be 50 ohms. Okay, then now we know that this is equivalent. This circuit here is equivalent to having two 50 ohm resistors in parallel. So we can work out what the green resistance is. So 1 over R effective is going to be, well, it's equivalent to having two in parallel like this. 1 over 50 ohms plus 1 over 50 ohms equals 2 over 50 ohms. Oh, I'm almost out of space, but I'm just going to get there in time. R effective equals 2 over 50 becomes 50 over 2, and so that's going to be 25 ohms there. And so this circuit here, which looks really ugly and complicated, is actually just equivalent to a circuit which is in series with 125 resistance. So 100, and then this whole section here counts as 25. Let me just... So we're looking at little nested sections, and we're taking each of those little sections and we're turning them into an effective resistance, and we're working our way outwards. Can I get whether that makes any sense? All right, I have one thumb up. Oh, two. Oh, excellent. All right, if I scroll down, it makes sense. Okay. All right. Okay, so then now we can use this to actually work out what is our current through the whole circuit, and then we might be able to work out voltages and things like that as well. Okay, so what I'm going to do is I'm going to work out that current by saying, okay, I have 120 volts on my circuit, and I have 125 total resistance. So the total amount of current coming through this whole circuit is going to be I equals 120 volts divided by 125 ohms is equal to, God damn it, I meant for this to come out to 120 ohms. That was supposed to be 1, but it's very close to 1. 0.96 amps. Okay? All right. So that's how we would work out the total resistance, and then therefore use that to get the total current. Okay, but that still leaves us with a little bit of a mystery in that we still need to work out what this inner current here, A2, is, because it's not going to be that full 0.96 amps. It's going to be some fraction of 0.96. It's going to be some split between the two different branches. And then we also want to work out how much voltage is getting dropped on that 150 ohm resistor. Right? Now, the way to approach this is to work out, is to look at your diagrams or your levels of analysis, and to say which one is going to be the simplest diagram I can use that gets me what I want. So we can't, if we want to know what the internal current here is on one of the branches, we can't use this diagram here, right? So if we're kind of looking inside this effective resistor, but we can use this diagram here, because that point there That's A2 there. All right, that's that point there. The orange can be treated as one resistor, and then we pass through our ammeter directly afterwards. Okay, so we can use this diagram here. And when we look at this diagram here, we say, wait a minute, I got 50 ohms here, I got 50 ohms here. If the two branches have equal resistance, then how much current should we expect to go down? What should we expect A2 to be?
Half of A total.
Fantastic, half of the total. So if A1 was 0.96, we're going to be expecting this to be 0.48. Now I will show you in a moment how to do one where those two are not equal. But for now, we can just say, oh, wait a minute, that 150 and 75 turned out to be equivalent to a 50. And if we have a 50 and a 50, then they're both just going to get half each. I really want to emphasize this because it's something that'll trip you up and make sure it's a nice little check, is notice that 50 ohms, the effective resistance of this section, is less than either of these resistors on their own. Because remember, resistance is how much we're stopping current. Let's imagine the 75 ohm is stopping at a certain amount. By adding on an extra 150 to the side, all you're doing is giving the electrons another path. So you're making it very slightly easier for them to get through. So you're dropping the resistance. So that's why we go down from 75 down to 50. Okay. All right. Lastly, let's work out the voltage on this one. Once again, we're going to look for the diagram. Even if you never actually physically draw these diagrams, you sort of the mental diagram, we're going to look for the mental diagram that lets us analyze the voltage across this resistor here without having to necessarily look at the complicated version. And what we're going to realize is this voltage here, using all the same rules that we've been applying in order to derive things earlier, that voltage here is actually the same as the voltage from here to here. Right? Because no voltage is lost in the wire here, and no voltage is lost in the wire here. So this point here is exactly equivalent to this point here from a voltage point of view, and this point here is exactly equivalent to this point here from a voltage point of view. So the voltage we get by measuring across this one resistor is exactly the same as the voltage we'd get measuring across this whole section. So we can actually use this really simple one down here. Will.
Can you connect a voltmeter to just two separate parts of the wire if you wanted to figure out what the voltage of the actual battery was?
Yes, absolutely. So it would have to be either side of the battery. But if you want to know if you wanted to measure, if you measured from that point of the wire to that point, then you would get 120 volts. But if you measured from here to here, then you would get 0 volts. Because what a voltmeter measures is not absolute numbers, it measures this difference between the 2 points. So if nothing's been used up between here and here, then you don't measure anything. But you will measure a big difference between here and here because the battery has given them 120 volts in between those 2 points.
Okay, thanks.
All right. So by sort of considering these simplified diagrams, we've realized that this problem here, which looks kind of tough, is actually equivalent to this problem here, which is fairly straightforward. And we can actually even apply Ohm's law to this bit down here because we know the current going through it. We have 0.96 amps going through this section. We know its resistance is 25 ohms. So V equals IR, it's just going to be 25 ohms times 0.96. And that, I can actually do that one in my head. That's going to come out to 24 volts. So V here is going to be 24 volts. Just using Ohm's law, V equals IR, but not trying to do it over here in this complicated version, 50 ohms times some unknown current, but doing it down here in the easier, more straightforward version. That said, though, we could, if we actually know that this is getting 0.48 amps, that means we also know that this side here is getting 0.48 amps. So we could say 0.48 times 50, V equals IR, and we'd also get 24 volts, exactly the same. Okay, so it really is, all of this stuff really is equivalent. When I say it's an effective resistance and equivalent resistance, I really mean it. Like all the maths works out the same. It's really lovely. Okay, what would we do if we weren't able to work out that 0.48 by just halving things? That's the only sort of thing we got left. So I'm going to do a slightly simpler diagram just so we can focus on that one question of what happens when these currents split unevenly. Okay. So let's just do a relatively simple. So I'm going to put my 120 volts back on. I'm still going to have this 100 ohm resistor here. But all I'm going to have in this second section is just 2 now, but they're not going to be equivalent. They're not going to be the same as each other. So this one here is going to be 100 ohms, and this one here is going to be 300 ohms. Okay. What I would like you to do for me is first off, work out the total effective resistance of this whole circuit for me. So do that by doing an equivalent resistance for any internal parallel parts, and then add them all together to get your total resistance. So work out that total resistance for me, and that's going to let us work out the total current. And I'll get you to also work out that one for me, please. So that's the current that we're going to be splitting into, let's call them I1 and I2. I'm going to give you 4 minutes to do that. Private message me in chat if you want a tip along the way. So first we're going to work out R effective of those two together, and then we're going to add that to this one here to work out the total. Sanka, right the first time. Oh, not the first time, the second time. If you've managed to get out R effective already and these two, then the next thing I want you to do is to work out the voltage drop using Ohm's law across that little effective bit. Okay. I know not everybody will be done with that, but we might, for the sake of making this video, not have 4 minutes of silence in the middle of it. We might crack on. So the first thing we're going to do is we look at this circuit and we say, what's the complicated bit? What's the bit that makes this hard? And it's this parallel section in here. And we say, okay, well, I'm going to redraw this circuit as the same thing, but I'm going to replace this complicated parallel bit with a single effective resistor. And so we're going to work out what is RF. Because these things are in parallel, the rule we're going to apply is 1 over R effective equals 1 over 300 ohms plus 1 over 100 ohms. And I look at that and I say, oh, there's a common factor of 100. So 1 over 100 ohms outside of a third plus, well, let's call it 3/3, 1. And so this is 1 over R effective equals 1 over 100 ohms times 4/3. Then we get R effective equals 100 times 3/4, so 75 ohms. That means our total effective resistance for the whole circuit is going to be, well, now this looks like a series circuit now, when we're going to have 100 plus 75, so 175 ohms. That means our total, if now we have our total resistance for our circuit, we can just use I total equals V total over R total. I told you electricity is full of subscripts. And so that's just going to be 120 divided by 175, which is 0. I don't know how many decimal points you want to keep, but 0.686 amps. Don't worry too much if you made some little error along the way, but that's where we're at now. And now the thing that we really want to work out though is, how does this 0.68 amps split up between this way and this way? Is it that this guy here gets almost all of it? Sorry, is it that this guy here gets almost all of it? You might have heard in sort of in year 10 electricity or whatever, oh, the electricity takes the path of least resistance. You've probably heard that term at least, path of least resistance. So you might think, oh, maybe all 0.686, maybe all of it goes through the lower resistance channel and none of it goes through the higher resistance. You might have also, you might say, oh, well, maybe it just splits 50-50. Maybe it's always 50-50. It turns out it's neither of those, and we're going to work out what it actually is now. The trick to working it out is to actually work out the voltage first. So if we work out the potential drop across that section, then we're going to be able to use V equals IR inside that section. So at the moment, I'm working out the voltage there. That's equivalent to working out the voltage difference between here and here on that original circuit. Okay, well, we can
So-
do... yes, Will? Was that Will?
Oh no, Lenuka.
Oh, Lenuka. Hey, Lenuka.
So you know how you got the total current,
Yes?
which is, can you work it out as a ratio, like 3:1 divided by 4?
I want to say yes. You can. So let me just say that.
Oh, okay.
But it's reversed from what you imagine. So it's not 3:1, it's 3:1. So this one has 3
Okay.
times as much resistance, so it has 3 times less current.
Yeah.
It is going to be that. It's always, the reason I hesitated before saying yes is people who try and use ratios in that way, it's absolutely right, but it's actually liable to cause more mistakes. For reasons that are maybe not super clear, but you just tend to make more mistakes when you're trying to approach that way. Whereas the way I'm going to show you is just a little bit slower, but a little bit more meticulous and make sure you get the right answer every time. So you're welcome if you're just confident using ratios, that's absolutely fine. But I do want to show you the more meticulous way. Okay.
Thanks.
So first off, we're going to work out what this voltage here is. So we've got 120 volts, but some of it is being lost in this resistor and some of it is being lost in this effective resistor somewhere in here. The way we're going to approach that is we just use V equals IR, same as we always do. Let me actually make this a pink one so that we have some distinction when we're doing our calculations down the bottom. So I want to work out what that V, and let's give it a subscript. Let's call it V, let's call it V1. Okay, so V1, okay. V1 is going to be, well, it's I through that resistor, so let's call that I1, times R of that resistor, which we've already worked out as effective. But because we're treating this now as a series circuit, the I through that resistor just is that full 0.68. It's got nowhere else to go. So this is going to be 0.68 amps times 75 ohms equals 51.43 volts on V1 there. I saw a hand go up. I don't know whose it was, but
Mine. So since voltage inside of a parallel circuit is measured as if it were like outside the 2 points of where it splits, does that mean if you just keep nesting parallel circuits within parallel circuits, the voltage will just always be the same?
yes. Unless the only thing that stuffs that up is if you then put like an extra series element inside as well. So if let's say we split this, I don't really want to draw on this again, but if as you're splitting, you're always just splitting, then yeah, absolutely. You just treat them all as being all equivalent voltage. But if you put even a single resistor before you split, then you have to go back to this nesting idea to work out effective resistances. Yeah. Because any two resistors in series are going to be sharing out the voltage. So if this guy here is getting 51 volts, just by the way, for completeness, then this guy here must be getting the rest of that 120 because the electrons going around have to lose 120 somewhere. Okay. So we got 51.4 volts there. And then we can say, well, wait a minute. If that was the voltage between here and here, that's also going to be the voltage between here and here. So we can work out what the voltage here is. That's also going to be V1. And equivalently, that one there is also going to be V1. Right? Because this point here has the exact same amount of energy as this point here, as this point here. If any points that are connected with a wire have the same amount of energy. Cool.
Sir,
Yes, Shangran?
would one like for both the resistors, why would the voltage be the same even though the resistance is different?
Fantastic, good question. They're in parallel, and remember, voltage is about how much energy each electron has at each position in the circuit. So if the electrons are moving around here, the current has 120 volts here because it hasn't gone through anything yet. Then when it gets to here, the electrons have some amount of energy. We don't know exactly how much. We've worked it out now, but we didn't know before, right? And that is a property of those electrons where they are in the circuit. It's about how close to home they are, right? So the closer they are to home, the less energy they're going to have. So it doesn't matter whether they went one way through the circuit or the other way through the circuit. By the time they get to here, they have, well, we can actually say now, they have 68.57 volts of energy left when they get to that point. And it really doesn't matter whether they went through this path or this path. We know that they have 68.57 when they get to the end. So that means the voltage drop in each of these is the same.
What if? Okay, so what if you were measuring the voltage like only across the resistor with 100 ohms? So
Like
would
this one
that
here?
be? Yes, sir, yeah.
Yeah, so these two
Both.
voltages will be the same. Now, what will be different though is the current. So this guy here will get way more current. So it's like, remember voltage, it's the combination of current and resistance. So if you have less resistance, but the same voltage, then you must be getting more current to make up for it. So it's almost like, yes, this is providing less intrinsic resistance, but because it has more electrons going through it, each electron is a little bit less reluctant because it's got the other electrons around it. So these two, the two that are in parallel, they sort of come to a balance. I've got more intrinsic resistance, but I've got more other negatively charged electrons running through me. So each electron, when it gets to here, is kind of like, which way do I go? Like, I don't really care either way. Okay. So we got 51.43 volts on here, right? Now we can apply that same 51.4 on each of these internal voltages. And we can say, wait a minute, I can apply V equals IR to these. So now I can use, if I want to find I1, I can use V1 divided by 300 ohms. And if I want to find I2, my voice just broke at the age of 34. If I want to find I2, then I can apply Ohm's law down here. So let's do that. Let's to finish this off. Let's make I1 is purple. So I1 is going to be, I'm going to examine this resistor here. So it's going to be 51.43 volts over 300 ohms equals, and I'm just going to leave that until I've done I2. And I2 is going to be in gray, and I2 is going to be that same voltage because these two are in parallel over 100 ohms So that's going to be 0.514 amps. And this one's going to be a third of that, but I can't do that in my head. So 51.43 divided by 300 is going to be 0.174 amps. Okay, so, and if we add these two up, 0.514 plus 0.174, we get 0.686, which is what we wanted. Yes, it's true that they don't exactly add up, but that's just because of rounding. If you took the full scientific calculator expressions, they add up. Whew. Okay, so in answer to Lanuka's question, absolutely yes. This one here ended up being 3 times bigger than this one here, and that's because the resistances are a 3-to-1 ratio. But and so that means this guy here got 3/4 of the current, this guy here got 1/4 of the current. You're absolutely welcome to use that if you want to, but just be aware that it does probably up your percentage chance of making a mistake by about 10%. So just just make sure you're being more careful about doing checking and stuff if you're going to use the ratio method. Okay. All right. Let me have a look at the time. It's almost 10:30. Yeah, let's leave it there.